A load balancer is a core component of any modern web application. In one or many parts of the application in a complex web systems, we are going to rely in a load balancer. I also believe that the best way that we can learn something is trying to build ourselves, and that's what I did. I implemented a lightweight version of a load balancer in Golang, and during this process I learned a lot of different stuff that I'd like to share with you. So let's go into the video. I'm going to split it in two parts. In the first part, we're going to take a look into the core concepts and talk about in a more abstract and theoretical way. And in the second part, we're going to take a look into the code and some code snippets and learn some lessons from the code base. So if you're washing dishes, we can listen to the first part without needing to look into the screen. Before moving to the video, please subscribe to the channel and like this video. This can help a lot. So let's go. A load balancer in a broader sense is the idea that we are going to distribute tasks across different computers or different threads or different executions, units of executions, units of processing. And in the context of web servers, that what we are going to focus in this video, we are actually distributing traffic. So a load balancer is any application that does that part. So for example, Nginx is a web server, but it also is a load balancer because within Nginx, we can distribute the traffic across different servers and different applications. So we kind of have some mixed definitions and products and services and applications that can do more than one thing, but the general idea with the load balancer is that idea of distributing that load. In terms of web servers, we need to talk about networking. So first thing that I'd like to discuss with you is which protocols we are going to distribute. So if we're running a web application, we rely in internet protocols. The most common ones would be the HTTP and TCP. So those are the protocols that are the foundation, for example, of REST APIs. Of course, we can have different protocols like UDP, for example, that will be used for streaming applications and other type of applications. But for now, we're going to focus in the HTTP and the TCP. So the first thing that I learned is that when you talk about load balancers, we can actually have two main types of load balancers. So load balancers that are implemented in layer 7 and in layer 4. And this terminology comes from the OSI model. The OSI model is kind of outdated for modern web applications in my opinion, but at least with TCP HTTP that makes sense, because in the OSI models we have those stacked layers when the top layers are built on top of the lower layers, and this is true for those protocols because HTTP is built on top of TCP. And with this hook, I'd like to discuss the difference between those different load balancers. So for example, when we talk about HTTP, we have a concept of a request. A request has a header, a body, and we can use that information, for example, within the load balancer to take decisions about how we are going to distribute and how we're going to decide for each server we are going to dispatch that incoming traffic. From the TCP perspective, we don't have this concept of a request. From TCP, we have connections that can be short-term or long-term. We are just dispatching those packets of information that may be or may not be related to each other. From the TCP perspective, we don't know that. So this is a really interesting trade-off that we have between TCP and HTTP. So with HTTP, for example, we can use the headers or a cookie, for example, to take the decision to redirect a same user to the same server, for example, and with TCP you will not be able to do that. In the other hand, with TCP, as we don't have to process an entire request, we're just working with this small segment of data and forwarding it, we'll have a better performance because we don't need to allocate memory to that, we need to do this long process and everything. So usually with TCP or layer 4 implementations of a load balancer, you'll have a better performance. And as I said before, the HTTP is built on top of TCP, so that means that a layer 4, a TCP web server, a TCP load balancer is actually going to work for HTTP requests, for example. So there is a lot of trade-offs involved on that, and this was a good opportunity to me to jump into this network internals and how that thing work. And going into the main the core idea of a load balancer, that is how we distribute, how we organize, how we decide for which server we are going to forward that request. We have a couple of options. Two main groups here would be the static ones and the dynamic ones, and of course we don't have only those three examples right here that we are seeing the screen, but I would like to discuss them because I actually implemented a lightweight version of that. So first with the round robin. So within the round robin, it is static because we are not relying in any of the specific data about each of those requests or connections on everything. Basically, with a round robin idea, we have a list of servers, and then we're going to, okay, first I need to server 1, then the next to server 2, then the next to server 3, and suppose we only have 3 servers, we go back to 1, 2, 3, 1, 2, 3, and we keep like cycling into that idea. That's basically what the round robin algorithm does. And we have another option that is hashing. So for example, we can use an hashing algorithm to always redirect a same user, and that could be going back into the layers. If you think about an HTTP request, we could use a user header to do that. So we ensure that the same user, despite of the network that user is connected at that moment or any other type of unique information like a MAC address or whatever, so we know that the same user, independent of network, device, and everything, is going to be redirected to the same server. With hashing algorithms, we can achieve that property, right? And for layer 4, for example, it would not be possible to do that. We could use, like I said, information like the local network, or maybe, I don't know if we could achieve a device information or everything that could be embedded into that TCP connection. And in the POC that I did, I used the IP address of the client that is sending it, but it's not perfect because if the user changed the network, or we can have multiple users in the same network, so we could overflow a single servers. There is a challenges involving that. So you notice that the hashing algorithms had different trade-offs and applicability depending in the network layer that we are going to implement that. So hashing is very interesting because of this property that we can send the same user to the same server, and we can do that without having any type of storage in memory or in persistent storage. We don't need that. Just the algorithm, the hashing algorithm, allows us to do that. And this is interesting because there is some applications that we could have some sort of in-memory storage in a server. For example, let's suppose that we have a shopping cart that is going to be stored in a specific server, and for that kind of solution we need to redirect the traffic to the same place. And in the dynamic ones, as the name suggests, we are going to use dynamic metrics to decide for which server we're going to redirect. And the one that I implemented is the least response time. So we are going to track the response time that we are taking to redirect for each one of those servers, and based on that information we can decide, okay, so I really have a fast server right here, so I decide to redirect to this server. If the server becomes slow, we'll have another server that will be faster than this one, and then we redirect to this specific server, and so on. So in that case, we can have a lot of different metrics. We can have metrics such as memory usage, CPU usage, or basically anything we want to do. So we kind of adapt to the data, the real-time data that we have regarding resilience and the operability of those servers. So for this example, I use the least response time. And here I come to a thing that I need to realize. So how am I going to compute the least response time? Because I mean, a load balancer is going to run basically forever. If it is not going to crash, it can run for months or over years. So we are going to store every single request indefinitely. We don't have infinite memory. So we have to have some sort of threshold, some sort of sliding window. So the first idea that I implemented is actually a Slido window mean algorithm. So basically, we keep the last n requests, for example, the last 10 requests for that server, and then we calculate a mean of the time, okay? And we use that to decide which server we are going to redirect. But there is some problems with that because in that example, all weights are the same. That means that the last request that was maybe a long time ago, it's continuing to impact at the same weight the calculation of the response time. We also have a challenge regarding the performance because as we need to store the last n values, we are going to actually use memory to do that. So that's another trade-off. And based on that challenge, I learned about the exponentially weighted moving average. So this is a concept. There is a mathematical formula equation that we execute that you can actually attribute weights to each one of the response times. And the idea with the exponentially weighted moving average is that the older values will have a lighter weight into the equation. So the newer requests, they have a higher weight, and that makes sense, okay? So if I have 50 samples, for example, and the last one that was a request from 8 minutes ago or 2 minutes ago, whatever, and this request was really slow, but the last two ones were really fast, that indicates that the server had a problem in the past, but right now, we are actually not facing any problem. But we cannot just using the last single value because network has problems and it can be just a invalid data point. So with the exponentially weighted moving average, we can achieve that idea, and we can of course use some specific value, because in the equation we will have a alpha constant, and you can change this value to give more weight to the newer ones or to the old ones. So it's something that is also configurable. And as this is an equation, we don't need to store the last n values. That's really, really, really interesting. The only data point we need is the previous mean for that server, a scalar value, not a list of the past ones. And then we calculate the equation again and get to the new value. We are going to see that into the code in more details. But this concept is really, really interesting. That is not the only place, of course, where we can apply this type of calculation regarding mean and average, but it was really interesting to apply in that specific problem of load balancers. And last lesson learned is regarding software design. So if you notice to each one of the load balancers strategies, we have the round robin, the hashing, the least response time, and we basically have the same interface. We have an input, we have the same output, but the strategy to tackle that is kind of different. And because of that, that's a good fit to use the strategy design pattern. It's a classical case that we could use that. So it was a good opportunity to me to review this pattern. I don't even remember when I was writing the code about it, but when I looked into the code afterwards, okay, that's definitely a strategy design pattern. So it is a good example for studying design patterns as well. That's one of the cases where we could apply it. This is my implementation. If you want to take a look in the code, quick comments about the repository and the implementation. I actually did it in Golang, and it was really interesting because compared to Python, which is the language that I use most of the time, my main programming language, Golang is more transparent in the trade also in working with networking, working with TCP. So I found that's really interesting to learn more about networking, for example, using a language such Go. So that was a good opportunity to me learn more about how handle errors and everything related to that. A quick comment about the strategy design pattern. So right here we have the function that based in an algorithm is going to initiate a specific type in Golang right here for each one of the algorithms that we are going to support, the round robin, the hash, and the new list response time. And that's all for today's videos, folks. I definitely recommend you to implement a load balancer yourself, or even any similar component that we can write and that is the basis for the computer science, because during that process we are going to learn a lot about the internals of that component, but we also have the opportunity to work with concepts that can be applied to other problem spaces as well. So the knowledge that we could learn from implementing it regarding the networking, the OSI model, the layers, and also the knowledge behind the math that we use to calculate the list response time can be applied to other problem spaces as well. So if you like this video, hit the button below, subscribe to the channel, and left some comments with suggestions, your opinion, and anything actually will help to keep this channel engaged and to distribute this video to more people. See you in the next video. Have a nice day.